How well do LLMs reason over tabular data really? By Cornelius Wolff and Madelon Hulsebos. Hello everyone and welcome back to the podcast. We often hear about how large language models, or LLMs, are revolutionizing how we interact with text. They can write stories, answer questions, and summarize complex documents. But what about data that's not just plain text? What about data that lives in tables like spreadsheets or databases, full of rows and columns, numbers and categories, where the relationships and meaning come from structure as much as words? When it comes to tabular data, are LLMs truly turning the tables on how we interact with structured information, or are they still getting tripped up by the details? Can we really trust these AI giants to perform accurate calculations or find specific information in a typical, messy real-world table? That's the core question this paper from Cornelius Wolff and Madelon Hulsebos dives into. They point out that while recent studies show LLMs can do some tasks with tables, we don't have a great handle on how well they really perform in realistic scenarios. Previous ways of testing LLMs on tables often had flaws. Some tests force the AI to give answers in a very specific format, which isn't natural and can cause errors. Other tests use multiple-choice questions, which can accidentally give the AI hints about the correct answer. And a big issue is that standard AI text evaluation tools like SakerBlue or BERT are designed for comparing long pieces of text. They struggle when the correct answer to a question about a table is just a single number or a short phrase, while the LLM provides a longer, more explanatory response. These tools can't reliably tell if the AI's detailed answer is factually correct when the ground truth is just a simple value. So, the researchers had two main goals. First, figure out a better, more realistic way to evaluate LLMs on tabular data tasks, and second, use that evaluation to see how robust LLMs are when faced with the kinds of imperfect data commonly found in the real world. For the evaluation problem, their key idea is to use an LLM-as-a-judge. Instead of relying on simple text matching scores, they use a separate, powerful LLM to act as a judge. This judge LLM is given the original question about the table, the AI model's answer, and the true correct answer. It's then prompted to carefully compare the AI's response to the correct answer and determine if it's factually right or wrong. They specifically used a large version of the Quen model as their judge and rigorously tested its reliability against human judgment, finding it to be highly accurate in correctly identifying right and wrong answers, which is crucial for trusting the evaluation results. Using this more reliable LLM-as-a-judge evaluation method, they reevaluated LLMs on an existing table question answering benchmark. And the results were quite eye-opening. They found that LLMs show a significant deficit in their tabular reasoning accuracy compared to what those same models scored using older, less reliable evaluation methods like multiple-choice questions. For example, on some calculation tasks like averaging or subtraction over larger tables, the accuracy measured by their rigorous method was 30%, even 60% lower than what the older multiple-choice tests suggested. This reveals that past evaluations might have significantly overestimated how good LLMs truly are at these tasks in an open-ended setting. Next, they wanted to see how these LLMs handle the messiness of real data. They took standard tables and introduced common real-world issues, missing values, where some cells were left empty, duplicate entities, where the same information was accidentally repeated in multiple rows, and structural variations, like shuffling the order of columns. They tested a variety of popular LLMs on different types of questions, from simple lookups to complex calculations, and on tables of varying sizes. Their robustness tests revealed several critical points. First, for most of the models tested, performance on reasoning tasks generally decreased as the size of the table they had to process increased. There seems to be a challenge for many models in handling larger contexts of tabular data effectively. Second, LLMs consistently found more complex reasoning tasks, such as performing calculations involving subtraction between columns or determining correlations, significantly more difficult than simpler tasks like just looking up a value or counting entries. Third, and perhaps most importantly for real-world use, the presence of missing values or duplicate entries in the tables caused a significant drop in accuracy for most models across many tasks. The LLM struggled to correctly reason when the data was incomplete or contained redundant information. Compounding this problem, the models often failed to acknowledge in their answers that the data was incomplete or had duplicates. This lack of transparency means a user might receive an incorrect answer without any warning about the data quality issues that caused it. On a more positive note regarding robustness, changing the structural order of columns had only a relatively small impact on performance for most models, suggesting they are less sensitive to simple visual rearrangements than to fundamental data quality problems. Among the models tested, GPT-4o Mini generally showed the best performance across tasks and was more robust to increasing table size compared to the smaller models. The implications of this research are significant. It provides a more realistic picture of the current capabilities and limitations of general-purpose LLMs when it comes to structured tabular data. It highlights that while LLMs are powerful for text, relying on them for critical data analysis tasks involving real-world, potentially messy tables requires caution. The paper underscores the need for developing more robust LLM architectures that can not only reason over structured data, but also handle common imperfections and, crucially, communicate transparently to users when the input data quality might affect the reliability of the output. In summary, Cornelius Wolff and Madelon Hulsebos' paper provides a valuable reality check, showing that by using more reliable evaluation methods, we see that LLMs still have substantial ground to cover to become truly robust and trustworthy reasoners over the kinds of tabular data that form the backbone of so much real-world information. It's a clear call for further research to build AI models that are not just great with language, but also genuinely capable with structured data, even when it's less than perfect.